Good morning, everyone. So, welcome to today's session on FPGA. Welcome everyone in the WebEx session as well as in the YouTube session. So, this session will be taken by Karan sir from my team, and along with him we have Isha and Hari over here. So, we will be starting the session soon. There are some technical difficulties, so once that is settled, we will be starting the session.
I hope I'm audible now. Hello?
Yeah, you're audible, but the
Hello?
audio is very.
Am I audible now?
Yeah, that's fine.
Okay. Um, is my volume too low?
No, it's fine now.
Okay. Yeah. So sorry for the delay. I'll begin with the presentation. I hope the screen is visible, right? To everyone? Okay. All right. So yeah. Welcome to this particular technical session of unveiling the FPGA. And I'm one of the Astro Tinker developers. With me, there are two more, Isha and Hari. So, yeah, let's begin. Before diving into this, yeah, does someone have anything to say? Okay, fine. Yeah, so before diving into this particular session, I would like to just get a quick heads up of how many of you attending this particular session know what FPGA is. Can someone write down in the chat or maybe unmute themselves? Any idea what FPGA is? Yeah, that's a filled gate programmable array. It's actually filled programmable gate array, FPGA, as it stands for. Uh, yeah. All right. So I'll. So the agenda for this particular session is basically we'll introduce you to what FPGA is in general. Then we'll show you a comparison between what an FPGA is with respect to uh, ASIC. ASIC is nothing but application specific integrated circuit, and a normal microcontroller that you would have used in some of your projects. Okay. Then we'll talk about the languages or scripting tool and some CAD tools through which we program the FPGA and what is its use. Uh, at the end, we'll talk about some of the applications of the FPGA, and lastly, we'll show a small application. So let's begin. So, what according to you is an electronic design? Uh, can someone write down in the chat? If you just go by the name of an electronic design, what does first come to your mind? Any ideas? Anyone? What is an electronic design? I hope there are electrical or electronics engineer people in the section right now. But yeah, it's a very general term, so it's not just limited to electrical people. Okay, I think people are shy to answer it. Anyways, so electronic design is nothing but in general, a process of developing a small circuit by using known electronic components in order to meet the given specifications. So I've highlighted two words in this particular sentence, and I'm going to talk about that. So specifications is nothing but a detailed description of desired behavior of a circuit. So basically, if suppose you are given a job of designing some circuit, who is giving you that particular job, you have to ask for a list of requirements and the list of specification what that particular circuit should do, right? Only then you can plan out, right, what components or what known electronic components I have to use in order to design that particular circuit. So that's why the other part is known devices. So devices whose behavior can be modeled by known equations or algorithms or with known values of parameters, right? So basically, an electronic design is nothing but a life cycle of the entire electronic products from right from the beginning of defining the specifications. Then you design the schematic, then you do a PCB design, then you go on for testing, and then you go for manufacturing. And if that particular device, after it is being manufactured, if it still has any defect or it's still not able to meet the requirements of the specification, you go back or you iterate your own design and you know uh, again start that particular process. So that's what electronic design stands for. So basically, it's a process of converting a behavioral description. So when someone gives you a list of requirements or list of specification, he or she is telling you that this is how that particular circuit should behave, right? And then you are converting that particular behavioral description of, in the terms of words, the specification in terms of words, into something, basically a circuit, which is a structural description of that particular specification, right? So after the conversion, after you have made this particular conversion, comes the physical design, which involves like choosing specific component sizes, their physical arrangement, and then defining the connections. So that's how you do. That's how you design the PCB, right? You create a layout of the schematic first with all the known components. Then you choose proper component sizes that are required. Then you make them or basically arrange them in a particular defined space, with making sure that the space is also correctly optimized. And then you route the signals or route the wires from one component to the other. All right. So in case of FPGA based design, like if someone asks you to design a circuit using an FPGA, in that case physical design is already done for you, and how it is done for you, we'll see that in the upcoming slides. All right. So yeah, this is all about electronic design, but you would have also come across the standard chips. Does someone of you know what are this 7400 series of chips? Has anyone come across this uh, ICs which are having the series name or series number of 7400 or 74XX and something? Anyone? Yeah, NAND gate. Yeah, so can you recollect or remember any of the uh, chip numbers in case? Anyone? So this particular 77400 series are basically a series of chips which are designed for uh, basic logic gates, right? So 7404 over here, as you can see, is a NOT gate IC. Then you have 7408 as a AND gate IC, and then you have 7432 as an OR gate IC, right? There are others as well for NAND, NOR, and up down counter, and so on, right? So this basic standard chips are responsible for providing you with basic logic gates, right? So for example, if you are asked to design some logic or digital circuit, you will use this particular ICs together and then design the connections, right? I guess some of you might would have done such experiments in your digital electronic course as well, where let's say you have to create a circuit for binary to gray converter, let's say. So you use this particular ICs and make such connections, right? Or if you are asked to design a multiplexer or demultiplexer using this basic gates, you use this particular series of chips and then make those connections. But are these standard chips the best choice to design any logic circuit or any complex logic circuit? The answer is actually no, because the function provided by this standard chips is actually fixed, right? and these chips are basically inefficient for building large logic circuits. As you would have seen in the slide previously, that let's say you have to just use two NOT gates out of the 7404 IC, you are still having an extra four NOT gate available, but you are not going to use them, right? So basically, they are going to consume much of the space of your uh, breadboard, where you are actually uh, trying to build your logic circuit, correct? uh, so then if you want to create a large logic circuitry, then there is a need for a chip which is suitable for doing that, where the structure of the chip is not fixed, right? So in 1970, actually, there was a chip developed called as programmable logic device, which is a general purpose chip consisting of a pool of logic gates and programmable switches. So basically, it's a kind of a black box like this. You can consider it as a black box for now, where you have inputs as a logic variables. That's how you have. That's how also you have in your normal standard chips, right? You have the input logic variables, and at the output you have logic functions, right? So for example, if you are using this particular basic logic gates to implement a full adder, for example, so you have the logic function output or the equation for sum and carry, but your input variables will be a, b, and carry in, right? So this PLD or programmable logic devices are basically a general purpose chip, and which has a combination or has a collection of many logic gates and some programmable switches. So these switches are nothing but they allow these gates to connect to each other. And how do they do that? I'll talk about this in the next slide. So one of the version or one of the type of PLDs is categorized into like simple programmable logic devices, and one of the simple programmable logic devices is PLA, which is nothing but programmable logic array. uh, so let's say you have to implement this particular logic function or boolean function, where f1 is x1 x2 plus x1 x3 bar plus x1 bar x2 bar x3. So what is this type of expression? Have you come across this word called sum of product and product of sums? Anyone? Yeah. So this particular equation that you see in the slide is sum of product or in the product of sum form. Yes, the other name is minterm as well. Yeah, so it is in SOP form, as you can see. So basically you have sums, which is nothing but an addition of some products. The products are this x1 x2, then x1 x3 bar, and so on. uh, Now if you want to implement these two boolean functions, and if we have to implement these two boolean functions in by using PLA, programmable logic array. So programmable logic array are nothing but basically it has, uh, as I told you, it's a type of PLD. So it will have some logic gates and some programmable switches. So which are the logic gates available in this? Are some AND gates are available, and then you have OR gates available. So basically this is called an AND plane, where you have a series of AND gates available, and then the other is called OR plane, so where you have series of OR gates available, right? So in the case of AND plane, each and every AND gate, uh, there are switches connected to as an switches connected before the input of this AND gate, and you can program these switches to turn on or turn off. Basically you can make or break the connection of this particular programmable switch over here, uh, and make sure that this particular line is connected to, let's say, x1, as you can see over here, right? I'll use the pointer to. So this particular switch you can program to make sure that it is connected to x1, and you can break this particular switch so that x1 bar is not connected over here, right? So this is how you create the products over here. So basically, if you want x1 x2, you will use this connection of these two programmable switches. You will turn them on so that x1 and x2 are connected. Then you have p2, which is, let's say, x1 and x3 bar. So you will connect those switches x1 and x3 bar. So basically you will get all these product terms available, p1, p2, p3 and p4, based on whatever you require as an output of your logic function or boolean function. And in the case of OR plane, again you have programmable switches available over here. You can decide which of these product terms have to be summed up, right? In the case of F1, you want P1, P2, and P3 to be summed up, but in the case of F2, you want P2, P3, and P4. All right. Sorry, my bad. P1, P3, and P4. Correct. So that's how you make the connection in the case of programmable logic array. So you have this logic gates available and the programmable switches. So this is a very detailed description of this particular PLA. In case of an abstract way, it is shown like this. Okay, so this switches over here, the access over here are nothing but connections which are shown that they are programmable. Okay, if they have a circle directly over here, it means those particular connections are fixed, they cannot be programmed. And that's what we'll see in the next slide. So the other type of SPLDs are PAL, programmable array logic, in which, for example, again, I'm taking two Boolean functions, let's say F1 and F2 over here. But in this case, the end plane is programmable, but the OR plane is fixed. All right. So basically, you cannot change the inputs of this OR gates. They are already fixed to, this two AND gates output. But all you can do is you can program the switches over here to make sure which product or which input should be given to this particular AND gate. Okay, in this case of P1, you are asking the product of x1, x2, and x3 bar. So that's how this P1 is created. And you want x1 bar, x2, and x3. That's how this P2 is created, right? And you have this particular OR gate which is already fixed, and that's how you get F1 over here. So why PAL is used instead of PLA is because when you have more and more programmable switches, it is hard to manufacture them as well, and it is not easy that the switches will work all the time when they are fabricated on the chip. So in the later years, PAL came into existence where they realized, okay, where they realized that the I would I request someone to mute. Can someone? Yeah, all right. So why this PL came into existence? As I said, because it is not easy to program manufacture these programmable switches. So they made that. Let's say we have the end plane programmable, but we keep the OR plane fixed. All right. So that's how this PL came into existence. But again, if you want to design large logic circuitry, you know, so let's say you have, for example, 100 input variables and you want to create more and more logic output functions or boolean functions out of them, it is not possible with this PL because you will require lots and lots of AND gates and lots of OR gates. So it is going to consume more and more amount of space on your chip, right? So that's how CPLDs came into existence. So after SPLDs, CPLDs are nothing but complex programmable logic devices, and they came into existence. And this is how a CPLD architecture looks like. So you have combinations or you have pool of PL like blocks. This PL like blocks can be a combination of PLAs as well as PL. Okay, in general it is called as PL. So it doesn't mean that only PL exists over here. It can be PLA as well. All right. So it's a combination of PL and PLA, and then you have a section of interconnection wires in between and some IO blocks. To have the input variables coming in at this IO blocks, and all these PL blocks are routed or connected to each other via this section of interconnection wires. So using the CPLD, you can actually realize a very big, a very large logic circuit. All right. So yeah, that's how the CPLD came into existence. But is that all? Like, still, is CPLD the best choice to, you know, design all kind of logic circuitry? Again, the answer is no, and that's how the FPGA came into existence. Uh, in case of FPGA, basically, you do not have basically like what the CPLDs or SPLDs have, like the pool of logic gates and then some programmable switches. No, in the case of FPGA, you have something called as configurable logic block, and in this configurable logic block, the basic element or the basic logic element inside this configurable logic block is called as LUT, which is nothing but a lookup table. Okay, so this is how basic logic block or basic logic element of CLB, which is nothing but configurable logic block, looks like. So you have a LUT over here, which is nothing but a lookup table where the inputs are coming. Nothing. This is same as your input variables again. Then you have one flip flop, and then you have a multiplexer. So basically, this flip flop is required to store the state of previous competition that this LUT has created. In case if you want to use this particular output of uh, LUT again as a feedback, so flip flop can help you in that case, right? So the architecture of FPGA is nothing but you have lots and lots of configurable logic blocks, and these configurable logic blocks are now connected to each other via switching blocks. So this section that you see over here, or this small square you can see over here, is nothing but a switching block. Again, this switching block is similar to what programmable switches were in case of PAL and PLAs, right? So you can program the switches and make sure that this wire is connected to this end, and that's how you can say that okay, this configurable logic block is connected to this one, let's say. So yeah, so if you open up the LUT again, this
Uh,
is how one LUT will
hello,
look like.
hello, sorry to interrupt. So your screen is not visible. Are you not sharing now?
uh, okay, let me share my screen again. I don't know why it stopped.
Yeah, it's
Is this
visible.
okay? Can someone give me a cue from where the screen was not visible? I can talk from that. Okay. Anyways, I'll repeat this part again. So FPGAs, the basic architecture of FPGA is nothing but you have lots and lots of CLBs, which is configurable logic block again. And inside one configurable logic block, you have LUT, which is lookup table, where you have the set of inputs. These are nothing but your input variables of a logic function or logic circuit, and you have a flip flop and then a mux, right? And then inside this pool of CLBs, how these CLBs are connected to each other are nothing but via switching blocks. So these squares that you see, small squares in the, this two-dimensional array of CLBs are nothing but switching blocks, and these switching blocks are nothing but a set of programmable switches, similar to what we had seen in the case of PAL and PLAs, right? So if you open up a LUT again, if you go deep into the LUT, this is how one LUT will look like. So as I said, you have an input over here as your Boolean variables, which is x1, x2, x3, for example. And since you have x1, x2, x3, you would know that maximum number of logic functions you can implement is nothing but 2 raised to 3 is 8 logic functions you can implement, right? So basically you have 8 set of outputs available, and you can choose what output your particular f should come as. So basically you have set of multiplexers inside one single LUT, and you can make sure that, let's say, for example, if I want to create a full adder, out of this single LUT. So x1, x2, x3. X1, x2 will resemble A and B, and x3 will resemble carry in, for example. So in this particular block, which you see over here, 0101, these are nothing but single 1 bit memory, or these are actually SRAM bits, static RAM bits. Okay. So you can program this particular bits either to make them 0 or make them 1. So if you want this F output, let's say to be sum, okay, what you will do is this one will represent x1, x2, x3 as 0, 0, 0. Then you have 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. The last one will be 1, 1, 1, right? So basically, you have to create a truth table of sum, and you will make sure that if you want the f as sum output, you will make this particular block as 0, because you know that if x1, x2, x3 or a, b, and c in are 0, the sum is 0. But if a, b, and c in are 1, which is the last case, the sum is also 1, right? If I'm not wrong. So that's how you make this particular sum output as 1. So what this entire programmable logic stuff means in general. So this is the hierarchy of digital logic, if you look it as at a very abstract way. So at the very top you have standard logic, programmable logic, ASICs, and full custom designs. So in case of standard logic, you have all these fixed standard chips that we talked about. TTL is nothing but transistor logic, and CMOS is nothing but complex metal oxide semiconductor logic, right? So you have 74xx standard chips, then you have 4xxx standard chips available, which is CMOS logic and TTL logic chips. And under programmable logic, you have all these categories that we talked about, like PLDs, CPLDs, and then FPGAs. And then you have another set called as ASICs, which are application specific ICs. And under them, you have gate arrays, and then you have standard cells. So we'll talk more about what are ASICs in the upcoming slides. And if you have full custom designs, like full custom design logic circuit, then inside that comes microprocessor and RAM. Okay, so let's compare now how the FPGA is with respect to ASIC and microcontroller. Let's begin with FPGA versus ASIC. So uh, yeah, so the left side is FPGA, the right side is ASIC. So application specific IC. So basically, when someone has to design an ASIC, or if you are given a list of specification to design an ASIC, uh, what the actual design flow would be. You would actually, whatever circuit you have to implement, as we talked in the first slide also, the electronic design process, you will create the layout first. You will make sure that your entire schematic is ready. Then you will make sure that what right choices of components you will take. Then you will make sure they are placed correctly. Then you will make the interconnections and so on. All that you can do it on FPGA first. Okay, so you will use an FPGA to make sure that this entire chip, what is it's supposed to do, you will implement that entire logic circuit in your FPGA. And once you have made sure that your chip is working correctly by doing the functional simulation or testing and verification on the FPGA, then you can move on to basically fabricate that particular design. What do I mean by fabricate? Is basically you can take that entire logic design and give it to a fab lab or a fabrication company who will manufacture your design on a chip. Okay, so once you are designing that particular circuit on a chip, that particular chip becomes an ASIC, because now that particular chip is specifically going to execute one single application that you have designed for. So that's why it is called application specific ICs. So that's why in the differentiation, as you can see, the time to market in the case of FPGA is faster, because if you have to just make a fast FPGA based design, you can basically uh, reprogram your FPGA to make sure that this particular circuit is working, even if it is failing. Let's say even if after the testing and simulation, if it is not matching the specification, you can reprogram the FPGA and test again, right? But if you have directly if you are directly going to manufacture the ASIC and then test after the manufacturing is done, if there are some errors in that particular chip, then you cannot go back, because there is much amount of time and money spent while designing an ASIC, right? And it is really costly to design an ASIC. So if there is some fault in the ASIC, the problem is you have to start again, and you have to incur same amount of cost once more. So that's why if you the time to market in the case of FPGA is fast, but it's slow in the case of uh, ASIC. Again, NRE is non-recurring engineering cost. as we talked about it, it is low in case of FPGA but very high in case of ASIC. The design flow is complex in case of ASIC, but it is simple in case of FPGA because you can easily reprogram the FPGA in order to make sure your circuit is meeting the specification. Yeah, but the unit cost of FPGA is very high, and in case of ASIC is very low. Unit cost is because the FPGA will take large amount of space on your fabrication chip, but if you are designing an ASIC, you will make sure that the chip is as small as possible. And when you are designing a ASIC, is basically you are basically charged for the amount of space in square you are taking, your chip is taking, right? So if you are designing very small amount of very small area of chip, the unit cost is also very very low, but it's not the case in FPGA. Of course, if you are designing an ASIC, the performance will be very high, but in the case of FPGA it will be medium, right? The again, in case of power consumption, in the case of FPGA, it's not every time that the FPGA will consume high power. It depends on what design you are implementing on FPGA. But in general, if you are going to compare FPGA and ASIC, it will be very low in case of ASIC because it is now very application specific. But in case of FPGA, based on your design, the power consumption can go very high as well. All right. Again, the unit size is similar to what the unit cost is as well. Like how much space it takes, it will be very low in case of ASIC, but in case of FPGA, it is medium, right? So this is a very general description or very general comparison of how FPGA stands out with respect to ASIC. Now, let's compare FPGA and microcontroller. Uh, so this is the differentiation. So in case of FPGA, as I told, you have configuration logic blocks, then you have all those programmable switches in between, right? So in case of FPGA, whatever circuit you are trying to implement, they are you know implemented in this particular set of or 2D two-dimensional area of this configuration configurable logic blocks. So all the boolean functions that you are trying to implement are implemented using the LUTs that we saw earlier. And basically it means that when you are trying to implement lots and lots of boolean functions in those LUTs, uh, you cannot have all the boolean functions implemented by single configurable logic block. Why? Because once over there, LUTs have maximum number of inputs as, let's say, 4 input or 5 input LUTs, right? So if you want to implement, let's say, boolean functions which are, let's say, greater than 2 raised to 5 or greater than, let's say, 2 raised to 10 or something, of course you will have to use more than one LUTs. But in the case of FPGA, what happens is all these configuration logic blocks are operating parallelly. Okay, so they are actually operating independent of each other. So in the case of FPGA, all these parts of circuit are operating independently. But in the case of microcontroller, as you would have already known, or if you have taken microprocessor or microcontroller class sometime before, you would know that you write or you program. You use software to program. Let's say you are using C or Java, for example, and you write your code or you write your logic in the piece of a software, and then you dump that particular software onto the controller, right? In the case of hex file, for example. And what this particular controller or microprocessor will do, it will execute the instructions which are present in one single hex file that you have provided one by one. It will execute the instruction from, let's say, int main to the last statement of the function which is written. Okay, so that's how this microcontroller will work. But in the case of FPGA, all the parts of this entire circuit are operating independently, right? In the case of microcontroller, you have fixed maximum clocking speed, right? You cannot go beyond that particular clock speed available. But in the case of FPGA, you can, based on your design, you can make sure that you have variable clock speed. Now, in case of microcontroller, again, if you have come across, let's say, 8051 or 8085 microprocessor, you have something called as ports available in them, right? So typically you can at a time access 8 pins, right? These 8 pins are nothing but IOs, input output. So basically you can access 8 pins at a time in the case of microcontroller. But in the case of FPGA, you can actually access many IOs simultaneously, right? Again, as I told, these IOs are also somehow connected to LUTs based on what design you are uh, trying to implement on FPGA. So since LUTs are executing simultaneously, or they are operating independently, you can access those IOs also independently. Now, in the case of microcontroller, because it is very custom, it is very application specific again. So the power consumption is very, less as compared to FPGA. And also you now have microcontrollers available with various sleep modes. So basically, if your particular controller is not supposed to do some job in a day, for example, it can go down to, power sleep mode and then come or wake up again in after some amount of time. But in the case of FPGA, based on your design, your power usage varies, but it is typically more than the microcontroller, right? Again, FPGAs are relatively costly as compared to microcontroller, and microcontrollers are cheaper. So yeah, this is how FPGA stands out with respect to microcontroller. So I hope you have a clear understanding of how FPGAs are with respect to microcontroller. So in very abstract form, if I have to tell you, the microcontroller will actually execute, or microprocessor will actually execute the code, or you have whatever software you have implemented on it one by one, or in a sequential fashion. But in the case of FPGA, you are not writing a software. uh, we'll see which particular language we'll use in the upcoming slide to program the FPGA. But using that language, all you are doing is you are actually writing the code, or you are writing the logic to program the hardware directly. You are designing the hardware in the case of FPGA, not the software. So that's the distinction between FPGA and microcontroller. And again, FPGA you can have blocks which are operating parallelly with each other or independent of each other. But that's not the case in microcontroller. So basically in FPGA you can harness the parallelism if you want, but that's not possible in case of microcontroller. All right. So now let's come up to what are HDLs, and we talk about some CAD tools and what are their use. Okay. So HDL stands for Hardware Description Languages. As I said, this languages or this is a specialized computer language which is used to describe the structure and behavior of any electronic circuit or any logic circuit that you want to design on FPGA, right? So what is the need for HDLs first? Earlier, circuits were designed on PCBs, right? But people used to design these circuits on breadboard first, and then once they have tested their design on the breadboard, they create a PCB out of it, and then they test and design them. But designing of these PCBs and testing and verification of these large circuits is not easy in case of PCBs. So what is the remedy for that? The HDL in this case make very easy to realize the hardware circuit on FPGA, because all you are doing is you are describing the hardware circuit in terms of a software logical algorithm with a particular syntax. Why syntax? Again, because it's a language. Of course, you have to follow some semantics and syntax to make sure that particular your program is converted into some particular file which will be dumbed down to an FPGA, right? And which particular tool will be used to actually convert this particular program that you have written into a hardware circuit? These tools are nothing but CAD tools, computer aided design tools, which generate the software or software which is describing the hardware circuit from the HDL that you have written. Okay. So we are going to the very basic or very famous HDLs available in the market, or they are very common to the public. One is VHDL, which full form is Very High Speed Integrated Circuit Hardware Description Language, and the other is Verilog. There are others as well. There are System Verilog, then there is T Verilog as well, and there are other languages as well. But VHDL and Verilog are very famous. Even industries use this particular languages to design logic circuits and realize them on FPGA. Yeah. So in this particular session, we'll focus more on Verilog because that's what we are, going to do in the Astro Tinkerbot theme as well. If you are participating in that, uh, so we'll just give you a basic introduction of what Verilog is, right? To just give you a flavor. So yeah, in Verilog, basically you can design your circuit uh, in different modeling styles. Okay, so one of them is called a structural modeling style. And again, uh, to be clear, this modeling style is not very limited to just Verilog. You can also do it using VHDL as well. So what is this structural modeling style? So this particular modeling style describes the connection of the components, you know. So basically, if you are given a particular circuit to implement, you will make sure you will be defining the interconnection of these components without actually explicitly mentioning that how these components will behave or how these particular components are going to work. Okay, so it is very easy to guess what will be the synthesis circuit out of this. So I know it is not very clear, but I'll take an example. So let's take an example of this full adder. I hope you would know, people who have seen this particular logic circuit of full adder. You have inputs of A, B, and carry in, and you have two outputs, sum and C out. But to implement a sum, the logic function is A XOR B XOR C. This is an XOR gate, right? And for the C out, it will be A dot B plus A XOR B dot C in. Dot means nothing but AND, right? It is an AND operation. So that's why you use an AND gate. So you have a C out as a another output of this full adder. Now, if you want to realize this particular full adder in structural modeling style in FPGA, so this is how you write the code. Okay, so this is a syntax basically of writing a particular code in Verilog. So you define the module first. This is the words that you see in blue over here are actually keywords like you have in your C program as well. You have int, void, and so on. Similarly, these are keywords in Verilog, but this is a customizable name. Okay, so basically you can write full adder or you can maybe mention full adder XYZ, whatever of your choice. So you define input A, B, and C in, and you have output sum and C out. Okay, so as I said, if you want to describe this particular circuit in a case of a structural modeling style, what you will do is, let's say you are defining some wires, let's say W1, C1, C2, C3, out one, some names, right? So all I'm doing is I'm creating a wire like this, focus on where I'm, keeping my pointer. So you are defining a wire for this, which is W1 in this case, and you are saying that I want to create a XOR gate, uh, okay, and W1 is the output and A and B is the input. Okay, so this will be W1. Now, if you want another XOR gate, you will write another statement XOR gate, and the output will be sum, and the input will be W1 and Cin. So that's how you want. Like this will be W1, and this is Cin as the input of the another XOR gate. So that's how you get sum as an output, right? So again, you will write so and so set of statements with and or logic gates to create a C out output. So basically, as you can see, you are describing this particular entire logic function or the logic circuit by actually defining the interconnection of these gates, XOR, and OR, how they are connected to each other, right? Without actually specifying how XOR works, or without actually telling how XOR executes, or what is the Boolean function of XOR, right? So this is what a structural modeling style looks like in Verilog. Let's go on to another modeling style, which is data flow. In the case of data flow, you actually express the flow of data using concurrent signal assignment statements. I'll tell you what this concurrent signal assignment statements in a moment. Uh, but in this case, uh, the synthesizable circuit or synthesizable circuit is not really easy to guess. Again, I'm taking the same example of full adder, and this is how you write a code for full adder in case of data flow modeling. So all you do is you use basically logic expression of whatever uh, boolean function you want to implement. Okay, so again, as you would know that this is a combinational circuit. Why am I saying combinational circuit? Because there are no sequential elements in this. Sequential elements consist of flip-flops and memories and so on. But over here, you can only see a set of logic gates. So this is a combinational logic block, right? So you can use or you can define the combinational logic output using assigned statements. This assigned statement is nothing but called as concurrent signal assignment statements in the case of Verilog, right? Concurrent, why? Because these will be actually executed concurrently. So it doesn't matter how you are, in which order you are defining this sum or cout. If you have 10 more assigned statements, it doesn't matter what is the order. All of them are going to be executed concurrently, right? So again, over here, you are actually specifying the logic function, but you are not specifying what this circuit will look like. So it is not easy to make sure you know how the circuit will look after the synthesis is done. All right, so this is a data flow modeling. Let's move on to the last one, which is behavioral. Now, as it goes by the name, in the case of behavioral, you are going to describe the entire behavior of the circuit without explicitly specifying the structure of the entire logic circuit. Okay. Again, if you are not specifying how the structure is, you cannot synthesize or you cannot guess the synthesizable circuit. So again, same example, and this is what the behavioral uh, modeling will look like in the case of Verilog. So you have A, B, and C, and you have to output sum and cout. But in the case of behavioral, basically you will use always statement, and you have begin and end. Okay, and over here in the at the rate you pass the parameters. This is nothing but called as synthesizable or sensitivity list. Pardon me, it is called as sensitivity list. So this always block is nothing but a kind of you can say a block which will be executed parallelly. And if you have a series of such always blocks available, let's say you are writing one always block for sum and you have another always block for cout, you know, these two always block will be executed parallelly at the same time, but the statements inside this always block will be executed sequentially. Okay, so in this case we are using case and case, and what we are doing is again, as I told you, in this case of behavioral, you are trying to express how this particular sum output should be. So basically this is nothing but the truth table, right? So you have 0, 0, 0 as an input, let's say A, B, and C. You want sum to be 0. And if it is 1, 1, 1, you want sum to be 1. Right? So that's how you are expressing the behavior of the sum output. Similarly, for the cout, you are writing the same, you are writing the truth table output of these particular set of input functions or input variables A, B, and C in this case. Right? So this is how you are using behavioral modeling style to describe a simple circuit like full adder in this case. I hope this is clear, like these three modeling styles, structural, data flow, and behavioral, right? Uh, yeah. So how will the actually netlist view of full adder will look like once you have written this particular Verilog code in either of the modeling style. But in the case of when you are designing a complex logic circuit, you can also make use of a combination of this particular modeling styles together to realize a logic circuit, because it's not always possible to write or design your entire logic circuit using exactly one of the modeling style, right? So in that case, you can use a combination of modeling style. So Verilog allows you to do that as well as VSDL. Yeah, coming back to what the netlist view will look like of a full adder. So this is how it will look like. Once you have synthesized, once you have written this particular Verilog code in a CAD tool, which is, let's say, quarters, for example. Once you synthesize this particular Verilog code, it will generate a netlist. Now, what this netlist is nothing but a connection or combination of basic logic elements that are available with the quarters, or which quarters can understand from what logic you have written, right? So let's say you have actually described your full adder in the case of structural way, it will design this particular circuit for you, and which is exactly same as you can see in the figure below, right? So because this is very simple circuit, full adder, all these three modeling style will be realized to same netlist view, right? So Quartus will actually design the same netlist view for you. Okay. Yeah. Now let's go on to what are the types of CAD tools available. So you have Quartus. I mentioned about Quartus, right? Uh, you have Quartus, then you have Xilinx. So Quartus is a tool provided by Intel. So all the FPGA ICs or all the FPGA chips or all the FPGA boards that are available in the market can be programmed using Quartus. Okay, so you can write the Verilog code, for Verilog or VHDL code for Intel-based FPGA systems. But you have to, if suppose you have to use some SoCs, SoCs is nothing but system on chips. If you want to use some boards or if you want to use some FPGAs which are supported by Xilinx, you have to use software which are supported by Xilinx. Okay, Vivado is one of the tools which is supported by Xilinx in that case. Uh, yeah, and the other tools are Synopsys and Mentor Graphics and Model Sim. The Model Sim tool is actually for simulation, and we'll talk about in the future slides why simulation is necessary. Now, the Cadence is actually very advanced tool, basically, where you can not only write a Verilog or VHDL code to realize the hardware circuit, but you can actually create a layout as well. You can actually design a schematic of what logic blocks or logic elements you want in your circuit, and then you can basically fabricate them as well. So that's why it is a very advanced tool. If you are asked to design an ASIC without realizing that on FPGA, you are supposed to use Cadence, and it is a proprietary software. So basically, you need to get a license to use this particular software, right? Yeah. So I hope these tools are clear to you. Let's talk about a bit on what are the applications of FPGA. Uh, so we'll talk about major four applications, but of course it is not limited to this four only. Uh, there is a plethora of applications in the world you can implement using FPGA. So one is, as I told, for chip design. Uh, you can realize your entire logic circuit of your chip on FPGA. Make sure it is working fine and meeting the specifications, all the functional specification as well as the timing specifications of your input design, and you can realize that on FPGA and verify that. The other is you can actually implement a CPU as well. Uh, just to give you an hint, we are going to attempt. If you are getting this particular Astro Tinkerbot theme, you will be implementing a very small CPU design as well in this on FPGA, and we'll teach you how to do that. So yeah, on using FPGA, you can actually design a CPU. You can write how the CPU will work, all the blocks of CPU, the ALUs, the RAM, caches, and everything. You can do that on the FPGA, and make sure that the CPU is actually able to implement the instructions that you are providing to it, right? In fact, the CPU manufacturing companies like Intel, AMD, and so on, they also use FPGA to realize their CPU designs first, verify their performance and speed and power and everything on the FPGA before they actually manufacture it in the fab lab. As I told you that NRE cost is very high in case of ASICs, so it is uh, desirable, or it is basically very advisable to implement your CPU design on FPGA first. The other application is ML and DL inference, machine learning and deep learning inference. So basically, on FPGA, because you have sets of configuration logic blocks available, all you can do is you can write the ML or DL code on some cloud platform, train your model over there, and take all your model parameters and implement, or you can say infer, your entire ML algorithm on the FPGA. And since on FPGA it will be actually taking lesser power, right? And also it will take less amount of space. You can do that on FPGA, as well as the speed will be faster if you are actually trying to implement that on case of in case of, let's say, a controller or processor, right? uh, the other application is robotics. Yeah, you can use FPGA in robotics as well, and that's what we are also going to do in this particular Astro Tinkerboard theme. So I'll not talk much right away for this application. We'll see that in the upcoming months, right? So let's now give you a small demo of application. But before we dive into that, I'll talk about what an FPGA design flow is, right? So in case of an FPGA design flow, these are the very primary steps, right? The first step is design entry. In the case of design entry, what you are doing is you are writing the HDL code, right? As I showed you in the previous examples, you will write an HDL model, and then this will be an input to your synthesize circuit, or basically a synthesis tool. So the HDL, or basically a Verilog or VHDL code, will be given as an input to your synthesis tool. In the synthesis case, it will realize it into the set of you know netlist of basically basic logic elements, and after that is done, it will be implemented on the FPGA. So basically, what does the implementation mean? Uh, Whatever configuration logic blocks are available on FPGA, right? As I told you in the case of in the earlier slides, as I told you that you do not have a set of logic gates available in the FPGA, like PL or SPL, CPLDs, right? You have LUTs available, and the LUTs are nothing but a set of inputs, and you have multiplexers available at the output. Uh, you are able to realize any logic function, using one single LUT. So basically, whatever logic gate your synthesis is able to provide you, whatever netlist that you saw in the previous slide, let's say XOR gate or AND gate or OR gate, it will be realized using this LUT, which is available in the FPGA, right? So that's what implementation means. And once this is done, you get a one single file, which is actually a bit stream file, and using that bit stream, you can program the FPGA. Okay. So now, uh, that's not all. But before you even get into the implementation, and that's why it's called behavioral simulation. So basically, you verify that your particular full adder is working as expected before it is synthesized into a netlist. After the synthesis, you again do the simulation to verify that, with more constraints of the specification, to make sure that the functionality of your logic circuit is as expected or is meeting what the specification is asking you to do, right? Now you add one more timing constraint on that after this particular synthesis is done onto the implementation. So basically, once this particular design of your logic circuit is fitted into the configuration logic blocks into your FPGA, you add the timing constraints as well to make sure that the sum and carry output are available at the required time as soon as the inputs are changed, right? There should be not much delay as well. If there is longer delay, propagation delay in your design, then it's not called a good design as well. So that's how you do. You have the timing simulation at the very end, because that's where your design is actually implemented on the inside the CLBs, or basically inside the LUTs, right? So this is a basic abstraction of how the FPGA design flow is. Uh, Now, again, very detailed description of SDL to SDL code to chip. Again, translate or synthesis is nothing but converting the SDL code into a circuit of basic logic elements. After the synthesis, you have something called as technology mapping. So, as I told you, post synthesis, which is called as in other words called as implementation, is nothing but it will take the input as a netlist that we saw in the previous slide, right, of a full header. It will take that as an input and it will try to realize that particular netlist using the components which are available on the target platform. So target platform in the case of FPGA is CLBs. So it will try to realize your particular netlist onto that target platform. And the collection of all the logic elements on any target platform are called as tech library. Okay, it's a very general term in the FPGA world, right? After technology mapping, uh, after the implementation, what is done is place and route. So you have once this particular logic function or logic design is implemented inside the LUTs, now all that remains is you have to program those switching blocks. You remember there were switching blocks available in between those in between those CLBs, right? So this programmable switches are, you know, the connection is made and broken using this particular placement and routing tool. It will make sure how these LUTs are connected, how the CLBs are connected with each other, and it will make sure that routing is as optimal as possible, right? So that the propagation delay is as small as possible, right? Longer the signal, like longer the signal route between one component to the other, longer is the delay, as you would know, right? So that's what the place and route tool does. And after this is done, basically the CAD tool, for example, the FPGA will generate a bitstream file. Okay, in the case of SOF, for example, or in the case of jig file, we'll tell you more in the case of the competition later on. But this is nothing but a bitstream file. uh, what this particular bitstream file tells is how this particular blocks inside the FPGA should be configured or should be connected to each other. Okay, and once you dump this particular bitstream file onto the FPGA, this configuration is made, and your design or the logic function that you want to implement is actually realizable on the FPGA now. So that's how this is the process, like how you write the Verilog code and how it is now implemented on the FPGA. I hope these steps are clear. Yeah. So yeah, one simple example that we are going to tell you about is mod 4 counter. So a mod 4 counter is nothing but, as you would know, it will count. Basically it will count, right? From 0, 1, 2, 3, and so on. Mod 4, why? Because it, when you say mod n counter, is nothing but this counter or this system will have n states only. Okay, so when you say mod 4 counter, it means that the counter is going to count only 4 states or up to only till 4. But now if it is counting from 0, what will be the max count? The max count will be 3, right? So it will count from 0, 1, 2, and 3. The application that we are going to show you today is basically mod 4 up and down counter together on the FPGA. Okay, so what does it mean by up and down counter? Just go by the name. Up means it will count from 0, 1, 2, 3. Again after 3 it will come back again and count 0, 1, 2, 3, and so on. But what does it mean by down counter? It will count from 3, start its counting from 3, then it will go down to 3, 2, 1, 0, and again it will go back to 3. So that's how it will count, right? So yeah, let's begin. So the SDN model of this simple mod 4 counter will look like this. Okay, now it is a counter. So basically it's a sequential circuit, right? And any sequential circuit, like let's say a flip flop, will require clock as an input. So you have clock as an input, that's all you need. And the output will be, one is the mod up value and the mod down value. Now why I am using 120? Because I just want mod 4, right? Basically I want only 4 states to be counted, and I can realize this 4 states using just 2 bits, right? If you have 2 bits, you can have 4 outputs: 0, 0, 0, 1, 1, 0, and 1, 1. So these are the 4 states. So that's why I'm using 1 is to 0, basically 2 bits for mod up and mod down, right? And you also focus on this. I have used REG, which is nothing but a register. So basically I'm defining 2-bit register. One register name is mod up. The initial value of this register is 3. The initial value of mod down register is 0. That's what we want, right? mod up should uh, uh, yeah, mod up should count from 0 to 3, and mod down should count from 3 to 0. Correct? uh, I think the statement is different over here. Yeah. All right. So in the case of, so how I have implemented this particular SDL model is in the using behavioral model, right? I'm using an always block, and at the positive edge of clock, whenever there is a positive edge of clock occurring, I'm making sure that the mod up value, the register of mod up should increment, right? After 3, it will increment to 0, 1, 2, 3, and so on. But in the case of mod down, right, it will, yeah, it will also increment over here. Yeah, just hold on for a minute. Yeah, pardon us for the okay. Pardon us for the typo in this particular slide. In the case of mod down, it should be minus over here because it has to count downwards, right? But yeah, there is a typo in just the slide. In the case of synthesis and the netlist view that we'll see in the later slides, you the code was written correctly. You can trust me on that for now. Okay. So yeah, this is the behavioral modeling style of writing a simple mod 4 counter. And after the synthesis, this is how it will look like, right? So basically you have two registers. Basically two registers means a register is nothing but a flip-flop, right? So if you have 2-bit flip-flop, you have one particular flip-flop over here, the other is over here, and you have clock as an input to both of them, right? And then you are providing, there are two adders as well, as you can see over here, right? So one will be outputting mod down, the other will be outputting mod up, right? Now in the case of functional simulation, this is how it will look like. So in the case of mod up, at the positive edge, you can focus over here. At the positive edge, at each and every positive edge, you can see the transition in both of the signals or both of these registers, right? Only at the positive edge, this transition is taking place. This X you can see, it is nothing but a transition of one particular state of that particular signal. So in the case of mod up, it is starting from 0 at every clock positive edge of this particular clock pulse. It is going from 1 to 3, and then once it is reaching 3, it will go back to 0 again, because that's the maximum count a 2-bit register can hold, right? Similarly, in case of mod down, it is 3 to 1 and 0, and again it will go from 3 to 1 and 0. All right. So this is how the functional simulation looks like. Now the technology mapping. So as I told you in the previous slide, uh, this particular netlist is nothing but how your sequential circuit will look like. But this is not what is available in the FPGA, right? You do not have flip-flops or you do not have directly adders available. You have configuration logic blocks available. So in the technology mapping, after the technology mapping is done, this is how it will look like. So there will be 3 logical cells, or basically 3 LUTs used by your particular design, by this particular design. And then you have some IO buffers as well. A clock is an input, so there is one buffer for here, over here. And then you have mod down and mod up output. Again, it is 2 bits, so that's why you have 2 small buffers over here for each bit, right? And these are the logical blocks after the technology mapping is done. And if you look at the place and route, after the place and route step, uh, this is very small section of, you know, how this entire FPGA is. And this is one configuration logic block, and you can see 3 rectangles highlighted over here, right? There are many white rectangles, as you can see in this other rectangles, but there are 3 highlighted rectangles over there. These are nothing but 3 LUTs. It says that your simple design or your logic design of mod 4 counter is using 3 LUTs of the entire uh, set of pool of LUTs available in this FPGA, right? So this is what the end, like one single application of your mod 4 counter will be realized onto FPGA. So yeah, so before ending this, I'll show you this. I hope you are able to see this. This is a small FPGA Intel D0 Nano board available. I hope you are able to see this, right? So you can see this. The left one over here is, I think is, hold on. Yeah, the left one over here is mod up, and the right one is the mod down. Okay, I'm not sure what's your right and left is, but this is the yeah, sorry, this is mod down and this is mod up. And you can see that the left one is the LSB in both the cases, and the right one will be the MSB in both the cases. This is an MSB. This is also an MSB. So in the initial it is going from 1 1 to 1 0 to 0 1 and then 0 0. And you can observe over here it will be initially 0 0, then 0 1, 1 0, and 1 1. Right? I hope this is visible to everyone. Is it visible, right? You can look at my video. I'm not sharing on the screen. You can look at my video in WebEx. All right, or maybe I can just stop sharing my screen because I'm done. I hope now you can see this. Okay, so this is a D0 Nano board provided by Intel, and the small Verilog code that you saw, we use Quartus to implement this on this particular FPGA. Again, we use Quartus because this is an Intel board. We have to use the CAD tool available with the card, with the which is supported by this particular board, right? So yeah, now the floor is open for question answers. If anyone has any question, we can answer that. I hope you are able to, you got a very fair idea of what FPGA is, right? Yeah, if you have any questions, I'm happy to answer them. Are we going to get the same board for the competition? Uh, Maybe I cannot answer that, but yes, you are going to get some particular some FPGA board for the competition uh, in the stage 2. If you are pass if you are getting if you are clearing the stage 1 of the competition, you will get the hardware, maybe this same D0 Nano board or some other FPGA board, but yes, you will get the FPGA board. Yeah. Any other questions? Please show that board again and explain. Okay. So I hope you are able to see this board. This is the Intel D0 Nano board, right? So as I told you, this particular application is the application that we wrote is mod 4 up and down counter. So basically it is executing both the logics simultaneously, right? Parallelly, it is able to implement mod up as well as mod down counter. But if you had implemented this using, let's say, microcontroller or microprocessor, you cannot see this uh, executing parallelly, right? Because it will execute the instructions in the sequential fashion. So one time it will do mod up, the other time it will do mod down. But you cannot see the states switching at the same time in the case of controller. But over here you can see this. Again, I will let me, yeah, the left one over here is mod down and the right one is mod up. So this one is mod up. Once it is 0 0 0 1 1 0 and 1 1, right? In the case of this one, it is 1 1 1 0 1 0 1 and 1 1 0 0. All right. Yeah. Tell something more about cadence. Cadence is a, what do you want to know about cadence? But cadence is a proprietary software. As I told, it is uh, only if you have license you can use that particular software. uh, as I told you that it is specifically used for implementing ASICs. You cannot use that for writing some code for dumping on FPGA. So in the case of Cadence, you are actually using you have a schematic layout. You actually place some MOSFETs over there. You make those connections. You use some tech-lib files that I told you, right? Which will basically have information about what will be the width and length of those MOSFETs over there, right? What will be the PMOS and also the power consumption, the delay, everything is defined in that particular tech library. And then you are actually verifying those particular designs in the Cadence itself. So basically, if you are designing a logic circuit, you can start from the schematic right down to the verification and simulation. You can test your entire logic design of your ASIC inside the Cadence tool before you submit your design to any fab lab for manufacturing. So that's why we use Cadence. Um, I hope this is the answer to like your question. Amit is asking how can we learn to simulate Verilog codes on FPGA board like just you showed to us. Uh, Simulate Verilog codes. There are online tools also available. Like I think there is EDA tool. EDA. I don't know. Yeah, EDA Playground is the website name. Actually, in that particular website, you can write the Verilog code and what do you say? You can see the output, like you saw the graph, right? I'll share the screen again once to tell you what I mean. The graph that you see over here, right? So in the case of EDA Playground website, you can write a similar code like this and see the output of functional simulation over there to make sure the signals you have defined in your particular logic design are able to switch the state whenever they are required to, based on whatever specification is that. So in this case, our specification was that at the positive edge of clock, we want the state of mod up and mod down counter to change their state, right? So that's what the specification is, and that's what we are also able to verify this from the functional simulation over here, right? So you can do that on the online tool of EDA Playground. Difference between CPLD and FPGA, as I had told before as well. In the case of CPLD, uh, so yeah, there is one particular term called as equivalent gates. In the case of VLSI design, equivalent gates are nothing but uh, the number of logic elements required to realize your logic circuit or the logic design. So in the case of CPLD, this term or this number of equivalent gates is very high because you have lots and lots of and OR gates available. As you saw that there are many PL blocks available, and then there are interconnections, and then there are IO blocks, right? So basically, you have lots and lots of equivalent gates available to realize a small logic design in the case of CPLD. And more number of gates means more space it will occupy on the chip if you are going to fabricate it, right? But in the case of FPGA, since you have very small amount of input LUTs, like you have max to max 4 or max to max 5 input LUTs available in single CLB, right? So you can implement small logic circuits inside that and also realize the entire larger logic circuitry because all these CLBs are connected to each other, right? Using those programmable switches. So the number of equivalent gates used to implement your logic design in case of FPGA is lesser in case of CPLD. I guess there are many Naruto fans in this particular crowd. I don't know why they are anxious about or very Naruto Uzumaki and yeah, okay, good. All right. There is a question how to program. Okay, how a program written on microcontroller can be implemented on FPGA.
Program written on microcontroller can be implemented.
I request to mute you, like mute yourself. Okay. So it cannot be directly translated because what you are writing in case of microcontroller is any C code uh, or Python code, for example, right? It cannot be directly translated onto FPGA because in the case of C or Python, you are writing a software, as I told you, correct? You are defining some variables, you are defining some functions, and then you are asking that particular what that particular function should do. But in the case of FPGA, the code that we wrote or the code that you saw in the case of Verilog or VSDL, you are actually writing the code to realize the hardware directly onto the FPGA. So the same thing that I showed you in the case of mod 4 and mod down counter, that you can do that in the case of C as well, right? uh, by writing some variables, and let's say you are writing a for loop, you can do that in the case of that, using some delay as well. In the case of, let's say, you are writing for microcontroller like Arduino, you can define that in the void loop function, and using the delay of 1 second, you can make sure that variable getting updated from 0 to 1 to 3 and so on. That you can do. But that's what uh, that particular code that you are writing is directly attached to one IO pin of microcontroller, and you will attach, let's say, an LED over there, which will toggle it from 0 to 1 and so on. But that's not what we are doing over here in the case of FPGA, right? In the case of FPGA, you are actually defining how the counter should work, because counter is a sequential element. What you saw in the case of synthesis is nothing but set of flip flops available, right? So that's how it is different from writing code from microcontroller to FPGA. I hope this distinction is clear to you. Could you just provide us an idea about the theme? How exactly will the astrobot astro tinkerbot theme, and what exactly we are going to do with this FPGA board? Again, as I told you, it's a robotic based application, and just one spoiler for this theme is, as I told you in the case of application slide, that you are going to realize one small simple CPU design uh, in this particular theme, and we'll show you how to implement that CPU as well. We are going to talk about some computer architecture world as well in the theme, but I'll not disclose much uh, because we are not allowed to, right? But if you are getting this particular theme, or if you are interested in this particular theme, of course you can select this as a preference, and we'll learn from each other in the theme, right? Is there any certification for this class? uh, there is a quiz coming up in the next 5-10 minutes. If you attend the quiz, and I don't know how much is the passing score, but if you attempt the quiz very well, you will be getting the certificate, I think. Where we can learn the Verilog language, there are many websites. There is a website called as FPGA for you. You can Google that, where there are many tutorials available to learn this Verilog and VSDL code languages. Then there is website called as nanland.com, again, to use to learn about these languages. But of course, if you are participating in this particular theme, you will be provided with resources and tutorials to learn this language. Can Arduino be used for FPGA? Of course not, because Arduino is designing the boards for microcontroller and microprocessors, and as you know that FPGA is very distinct from microcontroller and microprocessor. You cannot use Arduino to program FPGA, right? Like specific Arduino boards you cannot use for programming FPGA. Yeah. Any other question? And then maybe show. Uh, I think there is a query on YouTube which says that what is the, like, you want to know the glimpse of this particular EYC competition. So I better show you the website directly to. yeah, so this is, you can go up to this particular timeline and see this particular what this EYRC is. So it's a 7 to 8 month long competition, and there are two stages. uh, After you have registered and after you have been assigned a theme, you will be also asked for preference for a theme, right? uh, Once you have been assigned a theme, stage one will begin from September month. And in the stage one, you are provided with lots and lots of video lectures and tutorials, as well as small reading materials. uh, Basically, there is a hand holding session in this particular stage one, where you are actually learning by doing, right? You will implement this particular small task that we provide you at the end of, after you have read those reading materials and gone through the video tutorials. And if you are able to implement those tasks successfully at the end of stage two, at the end of stage one, you will be selected based on your performance. You will be selected into stage two, and in the stage two, you will be provided with the hardware, right? So we'll provide you a robotic kit, which is basically a free of cost. And this particular robotic kit is very specific with respect to theme you are participating in, right? So if you are taking Astro Tinkerbot, and like if you are being allotted Astro Tinkerbot theme, then of course you will be given an FPGA board and some other components to implement that particular theme, uh, right? And again, if in the stage two, if you are performing very well in the, like, the task like task 5 and task 6, which are the final tasks where you are implementing the entire theme run, if you are able to implement them successfully, you are actually called for the national finale at IIT Bombay, which happens in the month of March, right? And of course, if you are finalist, then you are also awarded with cash prizes and uh, internship, paid internship at IIT Bombay. So I hope that answers the query. Mm, yeah. Any other question on WebEx? How do I choose the right FPGA? What will be testing based on in stage one? How do you choose the right FPGA? Again, it depends on how many logic elements your FPGA, like your logic design requires, right? Uh, so different FPGA boards that are available in the market have different number of logic elements, basically. So the number of CLBs that I talked about, right? So that's what I mean by logic elements. So there are FPGA boards ranging from, having logic elements from, let's say, 5K to going up to 56K, and like more than that as well. Uh, the right now that I have in hand is, I think, having 60K around. Sorry, yeah, it has 22K logic elements, right? There is another board that we have in lab which is having 16K element, right? So based on, you have to actually design. So basically, I'll tell you one more thing. uh, uh, yeah, let me present over here once more. Sorry. Yeah, the SGL code that you are going to write in the uh, CAD tool, like quarters, for example. After you synthesize this and you are getting this netlist, there is something called as compilation report that is generated, right? So looking at that compilation report, you that particular report will tell you how many logical elements your design is taking, right? Also, it will tell you how many registers it is taking, how many memory bits it is consuming, and based on that particular report, you can actually figure out that what right choice you should make for, selecting an FPGA, right? Let's say your design is taking only 3K logic elements, so you can actually go with the FPGA board which is having, let's say, 5K or 10K logic elements, because your design can easily fit onto that. It's not worth investing money in taking a board of 22K elements, right? Because that will be costlier. So that's how you can actually select what particular FPGA board you should use for implementing your logic design. Uh, what will be tested in the stage 1. As I told you that you will be given some video materials and video lectures and some reading materials. Then there will be some tasks based on that particular reading materials. You have to implement that. Basically, you have to write Verilog code to realize that particular uh, set of specification that will provide you. And if you are able to write that particular logic Verilog code correctly, you are successfully completing that task. That's what we'll test in the stage 1. Yeah, all right. So if there are no more questions, are there any more questions? If there are no more questions, I think we can begin with the quiz. Uh, Let me take the quiz link. Yeah, just hold on. Okay. So yeah, I'm typing down the quiz link, or it is a Google form that you have to fill in the chat of the WebEx. So this is the quiz link. There's a question: what software is used for FPGA? As I told you in the slides of CAT, in the slide of CAT tools, there are many tools that are used for programming the FPGA. Quad Intel supports